Welcome to the Graph Show. I'm Josh Chinevere. I have with me today Scott Meyer from LinkedIn, distinguished engineer and architect of Liquid, the graph database that runs the economic graph. It's a database I've been interested in for a little while now. I think 2 or 3 years ago, there was a graph meetup where you presented on it, Scott. And I've gotten interested enough in graphs and metadata at LinkedIn that I joined LinkedIn a few months ago. So disclaimer, this is one LinkedIn guy interviewing another, but I haven't had much direct contact with Liquid yet, and that's going to change. So I thought this would be a good chance to bring you on the Graph Show and ask you kind of some newbie questions while I'm still relatively blank slate.
Cool. So, thanks very much. Welcome to LinkedIn, and I'm happy to be here.
Thanks very much. Thanks for being on the Graph Show. So I thought maybe we could just start with kind of the origins of Liquids, why Liquids, and maybe economic graph a bit after that.
Well, all of this started for me back in MetaWeb in 2005. And MetaWeb was building a world writable graph of all common knowledge. So spiritually, this is very close to RDF and the semantic web. So I spent 5 years at MetaWeb. Google bought MetaWeb. The freebase.com knowledge graph from MetaWeb turned into just Google's knowledge graph, also seeded Microsoft Satori. And I spent 4 years at Google failing to write a graph database, and then came over to LinkedIn and succeeded at it. So that's sort of how this happened.
So what do you mean by that? You wouldn't consider GraphD to be a graph database?
GraphD, that was MetaWeb's original graph, was a graph database. It had many of the features that we currently use. For example, it was log structured, but in other things, it was extremely nascent. There were lots of things. You could have links to links. It had a crazy and somewhat delightful Lisp-derived query language, and then we put a simpler query language called Mickle MetaWeb query language on top of that. That's very similar to GraphQL nowadays. So a lot of stuff was invented for the first time back there, and it's been considerably refined here.
Sure, that was one of the things that impressed me about GraphD way back in the day. One of the very first conferences I attended was the World Wide Web back in 2009, and I had a chance to talk with Jamie Taylor about Freebase, and learned that it had this neat feature that not many graph databases have, where you can kind of look back in transaction time and query the graph from a particular point in graph.
Yeah. So this is something that we've carried forward. Making things log structured is a fantastically good fit for knowledge. Knowledge is, say, data which is of interest to a lot of people. Knowledge doesn't change very fast, right? And is mostly constant. And so the cost of doing log structured is not that high. You don't get a lot of garbage. And when your source of truth is log structured, then you can just take a log offset and use that as virtual time. And so you can answer a question consistently as of any particular log offset or virtual time. So you can go back in time.
I imagine you could do the same thing using real time, right? If you were indexing on real time.
Actually, that's
yeah. Go ahead.
That's well studied in time series databases, and it's kind of tricky. You can, when everything works, But there's the problem with this is, well, what happens when you have some data arriving late? Then suddenly it's out of order.
It's not necessarily a bitemporal database. Would that be the? Right?
Yeah, I'm not sure what a bitemporal database is.
Okay. Yeah, my understanding of a bitemporal database is that you can query for using either transaction time or real-time event time.
Yeah. As I said, I think when everything works, it's pretty straightforward, and when things break, it's very hard. Right.
Well, cool. So assume we know a little bit about GraphD and Freebase. How is Liquid different? Compare and contrast. What's the delta?
Right. So the biggest delta is Liquid has a systematic answer for what we call compound edges. So in RDF, and edge is basically a triple, and Liquid starts off with that definition, but it turns out that not all relationships are amenable to expressing in a triple, right? Like a common one would be a film performance. You have an actor who performed a role in a film. That's three different entities. There are so we need a systematic way to handle that, and you can have 3 or 4 or 5 entities in these things, so the solution there is one to put an extra hop in the graph, so you have a central hub node with multiple edges radiating out from it. And then to figure out a way to compute the identity for the hub node such that the whole ensemble of hub and edges behaves like an edge. So that's the thing that's in terms of data structures, that's the thing that Liquid really figured out. And then in query languages, we moved from a language that we had invented to using Datalog, and Datalog is literally a textbook solution to querying databases. So you don't have to invent anything. You can just go to foundations of databases and read about it. This was just an enormous time saver in building this project.
Sure. A good example of kind of putting research into practice in industry, which I think I commented in our pre-chat. We don't see enough of that. Engineers don't seem to often be as aware of research that can really speed things along in terms of database and architecture.
It's something of a puzzle. I find it more and more of a gold mine. So many problems have been worked out and figured out that we don't have to figure out.
Sure. Can you tell us a little bit more about the data model? First of all, so compound edges, n-way relationships. Why could you not do the same in GraphD? Constructing them out of triples like you just described.
Well, you could. Theoretically, you could. Our triple was more complex, and so we were down the path of trying to make the triple more complex somehow, or have edges which referred to other edges. And this made the query language really complex to process and difficult to understand. But we certainly could have done it. There's no particularly great technical insight other than recognizing that, hey, I can create an identity for the node systematically, in a canonical way, such that the same edges will always generate the same hub node, right? That's really all it is. And as soon as you have that, then then any kind of compound behaves exactly like an edge. So it's sort of surprisingly easy. But you could have done this in Liquid. You can do this in SQL as well. The data model is very simple. The difficulty has always been querying it fast.
Yeah, got it. Seeing as it's a triple-based model, maybe you can compare and contrast it a little bit with RDF.
Sure. The spiritually very much the same. I would say the RDF triple has gotten very complex and asymmetrical, whereas Liquid's triple is really a triple of strings. And as we process them in the database, they are a triple of integers. The only constraints that we can put on these is that the literal strings can be required to parse in a certain way. So, for example, we could require that something parse as an integer. So you can say the subject of this edge must be a thing which parses as an integer, or the object of this edge must be a thing that parses as an integer.
And I imagine you can index them as particular data types too, right? So you can index integers.
Yeah. I mean, the contract with the database implementation is there's certain meta structure that the database knows about. So one of those are the scalar types, and then the database is free to optimize that. So, for example, integers are actually stored in line in the object reference, using a signaling bit. Mm-hmm. So you can operate on them very quickly.
Sure. You say it's the triples are symmetrical. By that you mean, for example, that a literal can be a subject, whereas it couldn't be an RDF. Is that what you mean?
Yeah, that's correct. So exactly, there's no asymmetry there. They're all the same. And in fact, in the code, it's usually a sign of a bug if there's any difference in the array position. So the code uniformly handles this as an array of 3 integers, and anything can be done on any offset in this array.
Sure. And I imagine there's no built-in semantics as there is with RDF. That's all application specific.
Yeah, I'm not quite sure what you mean there. I think we're talking about a distinction with RDF. One is we have only one metadata layer, which describes predicates and compound predicates as graph data. So the graph is self-describing. That's really the only semantic stuff that we put in. For the rest, it's just structure. The database doesn't care. So for example, any edge with a big fan in can serve as a type.
That brings us a little bit into types and type systems. So you mentioned scalar types. What about complex types? What about types that are defined, with reference to structure in terms of triples? Right.
So we don't have a statically declared type system. So you can't declare something. Well, this is an actor. This entity is an actor, or something like that. The observation I would make here is we have a query language that is as capable as a type system. And the query language allows you to say things like, an actor is an entity which has performed in a film or performed on stage. So your typing is just a matter of querying, right?
Sure. So yeah, more of a kind of schema on read than schema on write.
The schema is arguably always there. It's in the metadata. You just ask for what you want. right? We find that satisfactory. Like it's as capable as any type system. The distinction is basically the world of graph data is shared with many people, and no one user gets to say what can't exist, right? But people can say what's acceptable to them. For my purposes, I require an actor to have performed in a film or on stage. But you're welcome to take a more liberal definition or a completely different.
Yeah, and so you could kind of have different domain data models overlapping without any conflict, I imagine. So
yeah, that's kind of one of the strengths of a graph, is that you don't have to agree on the schema or the data model, and things can coexist.
Sure. Maybe can you tell us a little bit about the query language? It's Datalog based, but it's also a graph query language. What kind of specialization is there that makes it a graph query language?
Well, it's literally Datalog. I had settled on Datalog semantics early on, and I mentioned that to Andrew Carter, one of our engineers, and 2 days later he came back with a literal Datalog parser, and so that's what we used. So this is Datalog as you would find it in foundations of databases, that language. There, in terms of conjunction, disjunction, negation, there are no changes at all. It's completely standard Datalog, like you would read in the textbook. The approach to aggregation is somewhat different, but not particularly significant. And really, that's all you need. Datalog is fully capable of querying a graph. In particular, I think the virtue of it is that Datalog rules compose effortlessly. So this is much easier than SQL with subqueries or with
Sure.
views. The Datalog code is terse, and you can call other rules. And since our domain tends to have very complex queries, this is essential.
So to what extent is the query language aware that it's working with triples that are stored as opposed to quads or all the the various things that you could be working with?
Well, for the query language in the main, not at all. The two areas where you would see this are when you make assertions. The only thing that we can persist are edges. So all of your rules ultimately have to expand out to a graph of edges, which is the thing that we can persist. Yeah, that's really, well, the other place that you would see a graph is in the return value, right? When we evaluate a query, of course, you can return the bindings for the variables in the rule head. That would be a table. But you can also return the edges which produce those bindings. That would be what we would call a subgraph return. And if you, yeah, and the subgraph return, I think, is a key point in application programming. You really want a complex subgraph structure, and we'd really like to do this in one query. And so what we find in Datalog is a way to achieve that.
Sure. Some of the viewers are probably going to be wondering about property graphs. Do you think about property graphs as a data model? Like in particular, the one thing I can think of that might be challenging is edge properties.
Right. Okay. So a take on property graphs is basically a property graph is a wonderful index data structure, but it's not a very nice interface data structure. If you think about a property graph, I think the first question is, well, when do I represent something as an edge and when do I represent something as a property, right? And you have two different ways. It's not obvious which one you should use. So immediately it's harder to use, and it forces the user to make a decision that we don't think they should have to make. So if we look at nodes, all node properties are just edges. And any edge works just fine. If we look at edges, the triples themselves have no properties. But if you want to add properties to something, you create a compound edge, and this gives you an intermediate node. And then from there, it's just like a node. You can any edge off of the compound will serve as a property.
Sure, and that goes back to the symmetry that you mentioned. There's no difference between nodes and values. So there's no difference between edges and properties, data type properties, and object properties.
That's right.
All terms.
And then the sort of the follow-on points here. First of all, to a graph database, an extra hop can be very expensive. Like if you think about an application working with a graph of objects in RAM, people add extra indirection all the time, and they don't worry about it. Second of all, in the case of compounds, we actually know about the compound, and it's easy to add some extra columns to it, to its index representation. So we actually can deliver property graph performance without any of the syntactic overhead of specifying properties.
Sure. In the same vein, then, name graphs. Is it possible in Liquid to partition triples into graphs such that it's efficient to query, say, for all of the triples in a graph?
Yeah, we don't do that right now. We're exploring, sort of the simplest way to the simplest way to do that is just to give everybody separate predicates, right? And put everything in one graph, and that's basically what we've done. For one customer, that works fine. We're exploring more flexible ways of composing graphs where the graphs could be curated independently and could scale independently, but be queried together. Because some data is very hot and very big, some data is very hot and very small, and some data is very cool and very large, and you don't want the same replication applying to all of those.
Yeah, makes sense. In the solution you just mentioned, where you use different predicates in different graphs, so you just basically, if you wanted to query over multiple graphs, you just use a union of predicates.
Well, actually, if you want to query over multiple graphs, you just query. And if you want to limit yourself to one graph, you could say all the predicates from this source or all the predicates from that source. So the union's kind of pre-done.
Okay. Yeah, you filter as opposed to.
Right.
All right. Well, I want to talk a little bit about the economic graph. That's actually one of the things I know the least about right now, is how Liquid is built, how the economic graph is built on top of Liquid.
Yeah, I wouldn't say built on top of. The economic graph is roughly all of the data that we have. Most of this is offline relational data or document data. What Liquid stores is the kernel of that has to do a lot of joining online. So, for example, we do a ton of stuff with second degree connections. a recruiter will tell you that the value in the graph is not in your first degree, but it's in the second degree. So colloquially, your next job is probably in your second degree, it may not be in your first degree. So second degree in general is quite interesting. If you think about a human being looking at a large graph, one question that pops into your head is, well, what's interesting? What's interesting about this thing that I'm looking at? And usually this means, how does it relate to you? So if a person is looking at another person, did they go to the same school? Did they work for the same employer? Who do they know in common? Those are all very interesting things.
Sure. So you mentioned joining data. That's usually, I would say, the biggest challenge of building a knowledge graph. Comparable with the task of building the actual graph infrastructure is integrating data into a graph. So what is LinkedIn's approach to bring data into the economic graph?
Well, there are basically three things that you can do. Thing number one is you can have users curate the data directly, or you kind of people curate the data. If you have users, then they do that for free. And that works with some data. So people tend to curate their own connections pretty well, and they tend to curate their own profile pretty well. Other data, we would get commercial data from somewhere else and integrate it into the graph, and that would be a standard, data processing pipeline. Possibly have to work on record linkage, those sorts of problems. And then, of course, the third pillar is AI. Like we look at a bunch of signals and we try and figure out what we can know on the basis of that. And so the output of AI would typically go into the graph. And very commonly, this shows up as a score. Like, we think this is an important connection, or something like that.
Yeah, so tell us a little bit more about record linkage. That's kind of what I'm getting at as something that's often hard. How do you know that this entity in this particular table is the same as this other entity?
In general, that's an extremely difficult problem. I don't think anyone has any magic. Part of how we know things is just we have encouraged people over a long time to accumulate data. And one of the basic problems of record linkage is if you don't have enough data, it's just intractably hard. So if you're named John Smith and that's all we know about you, it's a hopeless problem, right? But if we know which geography you where you live, approximately even where you work, then we can start to disambiguate things. And obviously, if you have an exact match, there are various privacy-preserving ways of linking records where you use hashes of emails or hashes of phone numbers to determine if two things are the same.
Sure. Let's see. What are the why don't I ask, what are the hard problems in Liquid right now, or what are the things that are being worked on? What are the interesting problems from your point of view?
Query optimization is always an interesting problem. Our single node system is pretty good. Our distributed system is just starting to function well. So that's something we're interested in. We have also been very successful at LinkedIn. So we just got a rather large hardware bill for this year. and my boss informed me that next year we would be interested in efficiency. So we're looking at a lot of the index data structures, and are there more efficient ways to shard? Can we cut down the size of the indexes? All those sorts of things.
How do you prioritize what goes into the index and what doesn't? What goes into the graph and what doesn't?
It's really a question of utility. Do you? So we're trying to answer questions in human real time, roughly a quarter of a second. So like the first question is this index structure useful for answering queries in that domain? And for example, a lot of times it'll turn out that a large set, say 50 million things, is not very useful, right? Because it takes longer to materialize the set than any value you might derive from it. So a lot of the indexing techniques that we're looking at are how could we avoid materializing, say, large sets that we are never actually going to use, and instead get the query evaluator to recognize, hey, instead of asking about, say, Bill Gates's followers, we should ask a parallel query like, hey, everyone who's following Bill Gates, we'll look at this from the other end. And then we get free message passing parallelism. So 22x parallelism in the current system.
I see. I understand that Liquid is never the source of truth for the data that's in the graph. Is that correct? Are there plans to turn Liquid into a source of truth for some data? That different graph databases have kind of different philosophies on that. So I'm curious about that.
Yeah, I mean, our target is very large graphs. So if you have a very large graph, probably you're storing it somewhere. So durability is a well understood problem. There are lots of ways to solve it. On the other hand, querying a graph in real time is not a very well understood problem. So we specialize in that. However, that being said, we are kill 9 durable. So the entire database is in memory, in shared memory, but either the writer or the readers can be killed and be restarted, and the data will be consistent. So we're using two-phase commits to update memory. So I guess the colloquial way of saying this is an index which becomes inconsistent is not a very good index.
Sure.
Or another observation is if the index is providing the answer to the user, then it is a source of truth. So it better be accurate. So we actually have an internal customer inside LinkedIn, which is using Kafka as a source of durability. Obviously, you would never query by scanning Kafka. So all the querying is done through Liquid, and that's probably a route forward.
You give us an idea of the kind of the query processing time, like you're aiming for human real time or under 250 milliseconds or so. What about the scale? Can you give us any idea of the scale of
Sure.
the graph and what you think Liquid can scale?
We do, and in the current system, we have 22 1.5 terabyte shards in a single cluster. And of course, these are not all the way filled up. So we're looking at, 12, 13, 14 terabytes of actual data. Let's let's see here.
What that is in triples?
That in triples is, I believe, 200 billion triples, something like that. It's a lot. And then the production workload at LinkedIn runs about 1.5 million QPS. So we have a large number of clusters in 3 different data centers to handle that.
Okay. And what is sort of the anticipated scale? Is the economic graph going to grow? Does it have to grow?
Well, the anticipated scale is we're growing as fast as we can. So it's more predicated on like hiring people and making the onboarding process more and more self-service, and buying machines and putting them together, and yes, being more efficient.
Okay. All right. So it sounds like you haven't hit the scale limitations. In terms of
Everything.
data.
All of the software scales up pretty much linearly with cores. The real questions are, well, we have a lot of DIMMs in a cluster. So what is the mean time between failures that we actually experience, and can we repair clusters that fast? So approximately, we think we can grow by a factor of 4 or so with pretty much the same software. And obviously, we're working on improving the software. So yeah, the scalability is really limited by people writing code at this point.
Interesting. Well, I know you are going to have a talk at the web conference later this month. Anything you want to say about that? Kind of as a preview?
No.
Okay.
Come and listen to it. I will try and cover a bit more of this, maybe in a bit more depth. Yeah, just basic advertising there.
Sounds good. I'll be there.
Okay.
Anything else you want to say about kind of the future of Liquid?
Yeah. This data model and this query processing problem has been, I don't know, kind of an obsession, I think, for the past 15 years, and it seems to solve a bunch of very deep and long-standing problems in how you actually use a database to build an application, and it seems to be working. So it's super exciting, and I can't wait to see what happens next.
I agree. It's exciting. Yeah, I'm genuinely fascinated by your work on Liquid. So thank you for joining us, Scott. And
thank you.
This has been The Graph Show. Stay tuned for more episodes.